Okay, if you're in AP Biology or you're taking that class before, you know a little bit about chi-squared. So we're going to learn about the first part of doing a chi-squared test for goodness of fit. So the company that makes M&Ms claims the proportion of candy that is brown, red, yellow, green is 12.5%, and orange or blue is 25%. The hypothesis for a chi-squared for goodness of fit test would be the distribution of color in a large bag of M&Ms is the same as what they claim. There's nothing going on here. There's nothing unusual. The null is whatever the company claims the percentages are, that's what they are. They're not different than what the company claims, right? There's nothing going on here. The alternate is maybe you think the distribution is not the same. So this is different than the test we've been doing because in the past we've isolated one of the colors. Maybe we'd say, I think we did an activity where we did the blue M&Ms, right? We think the blue might not be the same percentage as the company says. Now we're saying all the color distributions for all the colors, we don't think it matches what the company says. So this is a different kind of test. It's a chi-squared test for goodness of fit. How good that the percentages fit the what the claim is, right? So you can say it in words. I think that's easier actually, or you could use like actual percentages there, but you don't have to state what each percentage is. So you can just kind of say the null is whatever the company claims, those percentages are true. The alternate is we think those aren't true. That's pretty much what the null and alternate are in whatever the context is. And so I like the way they said that last one. They said at least two of the proportions differ from the value stated by the null. That's typically kind of what we're looking for. It's hard for just one to be off, though. Does it make sense? Like, how could you have all the colors the same, but only one different? If you have at least two different, that kind of proves, yeah, it's not what they claim. Okay, so don't state the alternative in a way that suggests that all proportions are null. So it's possible like the blue is correct, but if all of them don't match, it's a no-go, right? So just be careful to say, say in such a way that they don't all have to be wrong to prove it wrong. We need at least two to be wrong, which is actually pretty easy to do, kind of. So don't write it like this. Right? Because then if one of them's true, you're like, oh, well, one of them's true. Well, I love this book. I read this book. So in his book Outliers, Malcolm Gladwell introduced the idea of relative age effect with an example from hockey. Many NHL players come from Canada, and depending on their birthdays, I think it was in January, like it was advantageous to be born in certain months. Because January 1st is the cutoff for birthday of youth hockey leagues in Canada. Children born earlier in the year compete against players who might be as much as almost 12 months younger. Gladwell argues that those relatively old players tend to be bigger, stronger, more coordinated, hence get more playing time, more coaching, have a better chance. So to see if the birth dates of NHL players are uniformly distributed across the four quarters, because if this theory is wrong, then you would expect the NHL players to have birthdays any old month of the year. If this theory is right, you might expect a lot more January birthdays for the NHL players than maybe any other month. So this is the distribution. Ooh, I think he may have a point. I think he may have a point. Let's see. Do these data provide convincing evidence? There's at least some evidence that tends to be a little bit more heavily birthdays towards the beginning of the year than that all quarters are not all the same. So what's the appropriate hypothesis here? We think that whatever the company states, in this case the NHL, that the birthdays will be equally as likely in any quarter. So all quarters have the same chance. The population proportions of NHL players born in each quarter are all the same. There's no difference, right? The alternate is, actually, we think maybe there will be maybe more players born towards the beginning of the year. In this case, So what's interesting is we don't have to, it's different than, remember how we used to give a direction to things? We don't have to do that with this test. So it's always like the company proportions are true, the company proportions are not true. They're not all the same, right? So in this case, all the same, but not what they stated they were. You could state it symbolically. That would be okay. So just give you different options there. You could define the parameter. P is the P quarter is the population proportion of NHL players born in a specific quarter. Calculate the proportion of players in the sample who were born each quarter. So what is the current proportion? So if you add those numbers up, that's like 52, 62, 68. I think there's 80 players. Oh, it says 80. 80 players altogether. So you could figure out the proportions here definitely don't match, but it doesn't prove it's wrong, right? There could be a little bit of randomness might explain a little bit of that, but that's the proportions don't match, so we have some evidence for sure. There is some evidence that for the alternate, because the sample proportions are not all the same. And we'll be able to calculate this in a minute. Today, it's just about kind of setting it up. So what kinds of things, what are the null and alternate? Calculate the expected count. So this is actually important to be able to do. So now we need to figure out the expected counts. And the formula is just n times p for expected counts. And so in this case, we expect all of them to be the same. So 25% times 80 each time, right? So N is the overall sample size, and PI is the proportion for category I specified by the null. So for each proportion, in this case, they're all the same. P is the same for all of them. It might have been different percentages, like the M&M problem. You would have slightly different proportions that the company was recommending. So calculate the expected counts. So you just take 25% or 0.25 times 80 and do that 4 times. And you'd get 20 each time. So we expect 20. We can see that we're right on the dot on April through June, but some of the others, not so much. Right, so those are all the expected counts, those are called. What are the conditions? So this may look familiar, random sample, we expect that, less than 10%, that should look familiar. This third one's a little different, and it's about counts, and it's about expected counts. So all the expected counts have to be at least 5. If you look back at our expected counts, they're all 20. That's good, right? So we want them all to be at least 5. I know it's kind of a weird thing. Be careful of the word expected there. So we want expected counts. We don't care what the actual counts were. It's the expected counts we are concerned about. That's exactly what the tip is. Be careful. Never round to the nearest integer. It's fine for expected counts to be decimals. That's not an issue. I would not round them. And make sure it's the expected counts that are at least 5. Check whether the conditions are met. So we already did the expected, random sample, perfect. Must assume that 80 is less than 10% of all NHL players, that's for sure. And then all the expected counts are at least 5. So, and you can just show that. You can show that in a list, in a table. There's lots of different ways of showing that, but all those are at least 5. Okay, that's the lesson for today. Again, we're just kind of setting the table for when we actually do the chi-square test, which is the next part of the lesson. A pretty similar example here with Reese's Pieces. The company claims it's 25% brown, 50% orange, it's interesting, and 25% yellow. But you're skeptical, and I understand. Sometimes you get a bag, you're like, this doesn't match that. So one statistics class bravely volunteers to open a party bag, 48 ounces of Reese's Pieces, selects a random sample of 125 candies. There are 32 brown, 66 orange, and 27 yellow. Do these data provide convincing evidence that the color distribution in the bag of Reese's Pieces is different than the company claims? So what's the appropriate hypothesis? So the null is the claim proportions by the company are the same, right? It's the same as distribution claim. The alternate is they're not the same, right? The distribution of colors, and that's a good word to use, the color distribution or the distribution of colors differs from what the company says. We don't even have to say which direction. We think they'll be more orange. We think, no, we don't need to do that. It's always just not equal to. It's not what the company claims. Calculate the proportion of each color in the sample. So if you know there's 125 in the sample, 32 divided by 125, 66 divided by 125, you'll just get those percentages. So we did that. They don't match. So, well, they don't match what the company claims. So we have some evidence. Well, so they didn't say the answer there. It was supposed to be the answer, I think, unless I copied the wrong thing. So because those don't match, that would be the thing. Because those don't match, we have some evidence for sure. A random sample of 125 Reese's Pieces is selected from bag. We already did this one. So the question was, calculate the expected counts. Okay, so how many would you expect? So 125 times 25%, 125 times 50%, and 125 times 25%. That's n times pi, I guess. So you do that 3 times, and you get 2 answers are different. So those are the expected counts. It's fine that they're decimals. Leave them as decimals. We like expected counts that are decimals. That's great. So those, they nicely laid it out, the observed. And sometimes the problem starts like this. Honestly, a lot of problems will say observed counts, expected counts. That's just your starting point. Check whether the conditions are met. So does it meet the random sample? Check. That was a random sample of Reese's Pieces. Less than 10%. We think that 125 is less than 10% of all the Reese's Pieces candies. And the large counts or expected counts here have to be at least 5. 31.25, 62.5, 31.25, all those are at least 5. And you just kind of list them out or say each one of them are greater or equal to 5. All those are okay. Good. That's your lesson for today.